Alright, hello, and this is the third video of my 5 videos on our physics articles that we did. So this particular physics article was called A New Law to Describe Quantum Computing's Rise. So this article gave a little timeline in Google's 3-month span from December 2018 to February 2019 of quantum computers' growth. So in December of 2018, Google used its best quantum computer at the moment and ran a calculation that was able to be reproduced by a regular classical computer, a laptop. Not the most powerful in the world, but it was in its infancy. So just 1 month later, in February of 2019, Google used its new beefed up quantum computing chip and ran a calculation, and it required a relatively powerful desktop to reproduce. Now, I'm sorry, that was January. Let's clear that up. So, let's retry this. In January 2019, it required a relatively powerful desktop to run. Now we're getting to February. By February of 2019, quantum computers in Google's home base had gotten so powerful that it required time on Google's server network of classical computers, regular computer chips, to reproduce, which at the moment runs millions and millions of regular chips. So, in this small span of about 3 months, Google was able to develop quantum computers far enough along that it took millions of classical computers to reproduce a calculation. Millions of classical computers. So, one of the lead researchers on this field, Mr. Neven, in the Google laboratories, created a law similar to the classical computer's Moore's law that describes the growth of quantum computers. Now, this Moore's law was developed 40 years ago by a man by the name of Moore, and his law stated, after observing the state of computers evolving over time, said that every 2 years, that's not 2 years, this is 2 years, every 2 years, classical computers will double in processing speed, and at the same time, in those 2 years, they will halve in cost of production. So this is already a ridiculous rate of growth. And to put this into context, CEO of Intel in the year 2015, CEO Brian Kurzanich stated that if Moore's law were to be applied to a 1971 Volkswagen Beetle the way it did to a 1971 computer chip technology, then today, 2015 at the time, you would be able to go 300,000 miles an hour in that Volkswagen Beetle. You'd get 2 million miles per gallon of gas efficiency, and this exact same Volkswagen Beetle would cost 4 cents, which is ridiculous. As we know, cars don't grow at a exponential rate. So, Neven's law is all the more ridiculous. Neven's law states that quantum computers, that's a W, that quantum computers will grow relative to classical computers at a doubly exponential rate. So Moore's law over here is a single exponential rate. Every year it doubles. So that could be shown by x to the power of y, where x is the current speed of the computer and y is how many years every 2 years, so it doubles. But Neven's law is slightly different and a little bit more ridiculous. Every 2 years, he states that it will grow at this rate with 2 exponents instead of 1. So to put this into context, like Intel CEO Brian Krzanich did, if we were to take a quantum computer that could run, say, 100 physics calculations per second, and that's not second, and we would apply Neven's law to it, our little doubly exponential rate here, for 10 years. The amount of physics calculations relative to a classical computer would end up being, after 10 years, it would be 442,449,673 times faster than a classical computer, which is already astronomical to begin with. So, say we want to add another cycle to this and add 2 more years. So, after 12 years, it would get even faster. And instead of being 42,449,673 times faster than classical computers, it would then be 1.84 times 10 to the 17th times faster than classical computers. And keep in mind, this is just 12 years. So two reasons behind this ridiculous growth rate, according to Neven, is one, which is where we get this y. Number one would be the growth rate of intrinsic growth rate of these quantum computers. They're being researched very heavily, so a lot of breakthroughs are happening in a very short amount of time. And like Moore's law, like normal computers, they're growing at an exponential rate over here. This is their growth rate. But where this second exponent comes in, the z exponent here, is because of a fundamental difference between the physical properties of quantum computers and classical computers. So, classical computers function using bits, trillions and trillions of bits. So these bits are tiny little particles that can be switched either on and off, and they can be either 1 or 0. And this is where we get the 1 and zeros code associated with computers, because in the end, computers are just running off of trillions and trillions of ones and zeros rearranged in order to create complex math equations, in order to display images on screen on the pixels, or to play video games. One of my personal favorites. So these bits can only have two states, 1, 0, and then they're rearranged to do all this stuff. Now, with quantum computers, on the other hand, they have these special bits called, I'm going to write it over here because I'm going to need space, qubits. Now, qubits function like regular bits. They're tiny little particles that move either back or forth to create a value between 1 and 0. But what's special about qubits is that they are they don't necessarily have to be either 1 or 0 like a regular bit. They can be superpositioned in between, anywhere between 1 or 0. So they can be in a state anywhere along here. And until you're to measure it or use this bit for any purpose, if it's in a superpositioned state, it'll be somewhere in between here. Once you measure it, then since just how quantum mechanics works, it has to collapse into either a 1 or a 0 state. It can't be both at the same time. Physics doesn't allow that. So it has to collapse. But before it collapses, it is in between any of these states. So you can create, say, 4 states rather than 2 out of qubits. Unlike regular bits that only have 2, there can be 4 states. You have your 1 and 0 where they're absolutely either 1 or 0, or you have these special states of, let's call it 1b and 0b, in which it was superimposed along somewhere between 1 and 0, and then when observed or used, it collapses into the state. 1b is when it has a higher chance of collapsing into the 1 state, and then we get a 1b. 0b is when it has a higher chance it's further along over here rather than over here, and the bit collapses into the 0 state, which is a different state altogether than just 0. So we can measure whether it was previously superimposed or just 1, meaning that we can use 4 states instead of 2. So this means that if you were to have 4 quantum bits, 4 qubits, it would be equivalent to 16 regular bits, because unlike regular bits, it has 2 times the number of positions it can be in. And another way to say 2 times 2 would be 2 squared, which is where we get this z exponential. And that is how we get the 2 different exponentials, the doubly exponential growth rate of Neven's law. But, oh, wrong thing, eraser. But just like all new theories, there are critics, me being one of them, of this new Neven's law, because Neven's law is one, very new, so we haven't had much time to play around with more with quantum computers as we have classical computers. With classical computers, we've had 40 years of measurement behind it, telling us that yes, this Moore's law seems to be relatively consistent. So we have proof behind it. However, with quantum computers, we don't have that consistency, those years of consistency we can measure. So it could definitely be a different rate of growth. And 2, with the amount of breakthroughs going on with quantum computing at the moment, it could definitely be a completely different rate of growth. What if it's an exponential rate of growth but to the 3rd power rather than doubled? Or what if it's slower than a doubly exponential rate? We don't know that. And the last gripe that other scientists have said against Neven's law is that, or not other science, me particularly thinking about it, is that Neven's law, unlike Moore's law, is actually measuring two variables together. So the variable x can represent quantum computer's rate of change. That's a G. Quantum computer's rate of change. And that would be versus our y here, which is classical computing power. But these are two variables. They're not constants, because classical computing power still adheres to Moore's law. It is still changing, it's still getting better over time. So this doesn't stay consistent, so it's not really good as a measurement of, say, change, because it's not a constant value you can measure to. With Moore's law, it's simply measuring one variable to a constant. So x here would be classical computing power, and then the y here would be the ability to do equations. Let's call this 1 plus 1. The power required to compute 1 plus 1 never changes. It's always going to be just as hard to compute 1 plus 1 50 years from now as it is today, because it's just 1 plus 1. It's a constant, unlike classical computing power, which constantly changes. So that's one of the fatal flaws I see with Neven's law, is that 40 years from now, if we were to use Neven's law, if it were, say, 100 times faster than classical computing power, that doesn't really mean, we can't say that's consistent, because what if 10 years ago classical computers were only were 1/5 the power they were? So it can't really be used as a consistent measurement. So that's all I have to say personally about it. I was sort of going on a spiel about Neven's law, but the overall goal in this field of quantum computing, the overall goal of why people are trying to develop all these rules, such as Neven's law for quantum computing, and they're still attempting to continue working on quantum computing, is in order to reach the paramount, so let's call it apex of quantum computing, which would be termed quantum supremacy. Which is a fancy way of saying that the time that quantum development reaches a state in which we can do a mathematical equation, put a real world use to quantum computers, that there is no classical computer or no amount of classical computers could recreate it in any good amount of time. It would take 1 trillion years for a classical computer to do this. So that's what is meant by quantum supremacy. And that is what everyone is trying to run towards with these quantum computers. Since quantum computers, as we've seen, are inherently better than classical computers because of their double states of bits. I think I might have erased it. No. But their double states of bits, having 4 states instead of 2 states, then that means that they can be used to eventually create some extremely powerful computers. And that would be everything I have to say with this article. So, a lot of my questions, I don't really have any questions with this. I had more sort of complaints, and the questions I did have were stated over here in the sort of critiques of Neven's law. I'm the one who thought about the comparing two variables together. It wasn't said in the article. I was thinking about it, and it just doesn't make sense comparing two variables together as a law. It simply doesn't make sense. And that would be it for me. So that's the end of my recording. If I could get this to work. Thank you.